All right, so I got a new document camera. Hopefully this helps us work these problems without having it so laggy and all that kind of stuff. But this is a worksheet, Chem 820. That's a grad level class that I took. So like after you have a bachelor's in chemistry, where we certainly did some stuff harder than this, but as our intro to redox stuff, they gave this homework assignment. And as I was going through the homework assignment, I was like, this is a great assignment. I should have my AP Chem class take this. So anyway, we'll go ahead and work through these as some practice problems. And it would be great for you to try and do these on your own first, if you're starting to feel comfortable with some of this stuff, and then work through these as reinforcement. With me showing you how to do them, or you could, if you're feeling kind of lost, go ahead and have me walk you through them and that kind of stuff. Anyway, going to number 1 here. How many electrons are transferred in the following reactions? So we're wanting to know basically when you split this into 2 half reactions, what's the number of electrons that are going on there? So we have Cr2O7 going to Cr plus 3. So here you have a total of plus 6. Here you have minus 14 from your oxygens, and you have overall it's a negative 2, so this must be plus 12. Oh, that shouldn't have a 2 there. That's a typo. I think I forgot about that. But anyway, so these must be plus 12. So plus 12 to plus 6, that is going to be 6 electrons getting transferred there. You want to think in terms of total electrons, not each of these chromiums is plus 6 and then goes to plus 3. But overall there you do that. We could also do it in forms of this, where this is minus 1, minus 1, minus 1, minus, 6 minus 1s. Is that 6 of them? That's 5 of them. Over here to 0. So here this was 6 electrons to 0 electrons, right? So either way, you're talking 6 electrons. Right? Okay. Which metal, aluminum or nickel, could reduce zinc plus 2 to zinc? So we look at this and we say, well, these are written as reduction potentials, right? This is zinc gaining an electron. Leo said lose electrons oxidation, gain electrons reduction. So these are all gaining electrons. So these are all written as reduction potentials right now. So in order for zinc to get reduced, that's a negative 0.76. Remember, we want delta E's to be positive for it to be a spontaneous kind of thing. So that means if I'm going to make one of these others do that, I'm going to have to flip it around. So if I flip the nickel around and make that positive, that's still overall a negative. But if I flip the aluminum around, aluminum is reactive enough that it could force zinc to go into zinc metal, right? Like in first year chem, we had our reactivity series. This is just a better version of a reactivity series, right? So if we flip the aluminum around, aluminum metal could take zinc ions and force them into zinc metal, right? Like you probably remember we took zinc a few times and reduced copper back to copper metal, because I don't know what copper's thing is off the top of my head, but aluminum could do that, right? Question number 3. Which of the following is the strongest oxidizing agent? So we want it to be we want it to be good at being reduced itself. So it needs to be gaining electrons. All of these are written as reduction potentials, right? There's so many little places where you can make a mistake. So I always try and be real systematic when I look at these. So these are written as reduction potentials. So then we just want the biggest positive value for the reactant. Now it's MnO4 minus. So this is the biggest positive value, but this is the oxidizing agent, not this. This is the pair of things, right? Is MnO4 minus to MnO2, but the oxidizing agent is the MnO4 minus, right? This would be the best oxidizing agent. This would be the second best oxidizing agent. Oh, no, sorry. That wouldn't be the second. Zinc, if you flip this. Oh, no, because then that's not a reducing agent anymore. Yeah, so or an oxidizing agent anymore. So zinc plus 2 is just a terrible reducing agent, right? Or oxidizing agent, because it doesn't really want to get reduced. So the next best would be I2. This would be the second best. None of the rest of those are really good oxidizing agents, right? So as it's written, this is a big positive E. So that is the thing getting reduced, and it is good at that, right? So it can force other things to be oxidized. Okay, number 4, is that fuzzy? I can't tell if that's fuzzy or not. What if I just hit the autofocus button? Maybe that's a little better. Okay, 4. The following half reactions take place in a galvanic cell at standard conditions. What species is produced at each electrode? So they're wanting to know who's your cathode and who's your anode and all that kind of stuff. So we need a positive here, and we need one thing getting reduced and one thing getting oxidized. So this is the one that I'm going to flip because I want overall this to be positive. So when I flip this, it's going to be Sn goes to Sn plus 2 electrons. No, electrons have a negative charge. Heard it here first, right? So we flip that around. So this would be our thing getting oxidized. This would be our thing getting reduced. If we wanted to put this into line notation, it'd be Sn plus 2, salt bridge, Cu plus 2 to Cu, right? That would be that in line notation. They didn't ask us to do that. We haven't done a lot of those, so maybe that's helpful to you. So we want to know what's produced at each electrode. Well, this is losing electrons. So this is the oxidizing part. So that means this is the anode, right? So this is the anode because oxidation happens at the anode. Remember the vowels. Oxidation, O, happens at the anode. Those are the two vowels. Reduction happens at the cathode. This is reduction because it's gaining electrons. So the products are my Sn plus 2 and my C, right? Remember we run reactants, products. So that's the product at the anode. That's the product at the cathode. So I need Sn plus 2 at the anode, Sn plus 2 at the anode, and Cu, just Cu metal at the cathode. So D is the right answer for number 4. Let's see, we're 6 minutes in. So we'll get through what we can in not too terrible a day. Let's see, number 5. Let's move this guy down here a little bit. Which of the following is the best reducing agent? So now a reducing agent is something that wants to be oxidized. So now we're going to be looking at one of these products should be our answer. So if I see Cl2 in here, it can't be that. If I see Mg plus 2, it can't be that, right? Because these are written as a reduction. So those would be an oxidizing agent. So it has to be one of these three. When we flip them, we flip the signs. So this would be negative. Well, that's just everybody's based on that. This becomes a positive then. So this one is the best thing at being oxidized. So it's the best reducing agent. And that makes some sense because I know magnesium loves to burn and catch on fire and be oxidized by oxygen, right? We've seen that happen. So magnesium is a good reducing agent because it's good at being oxidized, right? So magnesium is our best reducing agent of those things, right? It can force other things to be reduced while it is oxidized. 6, the standard potential for zinc plus silver goes to zinc plus 2 and silver is 1.56. Given the standard reduction potential for silver is this, determine the standard reduction potential for zinc. So as this happens, it is the reverse of this, right? See, I have zinc metal going to zinc plus 2. That's flip-flop of this. So whatever's happening here, so I'm going to, when I add these two reactions, when I add the silver reaction, which is 0.8, plus the zinc reaction, overall, that's going to give me a 1.56. That's 0.76, right? Let me double check, make sure I'm not doing stupid math in my head. So that means the zinc one, so if I do 1.56 minus 0.8, right, just math there, then the zinc one must be 0.76. But whoa, careful. This is zinc getting oxidized. They want to know the reduction potential of zinc. So they want the flip of this reaction. So it would be a negative 0.76, right? That's an easy place to make a mistake, right? Keeping track of directions on this stuff is valuable. All right. Consider the electrochemical cell with a copper electrode immersed in 1 molar copper and a silver electrode immersed in 1 molar silver. So this is not an Ernst equation kind of thing. This is just a standard electrochemical cell. They want to know what the cell potential is. Well, the one that's going to flip is going to be your copper one is going to flip. So we're going to go from copper to copper plus 2, salt bridge, silver to silver plus to silver. In the Nernst equation, I will care about the 2 electron situation here, but in a standard cell, those electrons move one at a time, and so I don't care about those, right? That number of electrons only comes into play in the Nernst equation. So I have to flip this sign, so that's going to be a negative, so we're going to do 0.8 minus 0.34, and that is going to be 0.46, which is D, which works out. Right? Which of the electrodes is the anode? Which of those is the anode? So anode oxidation happens at the anode. So that's the one that we flipped. So the copper electrode is the anode. The silver electrode, we have reduction taking place. Reduction happens at the cathode, right? Keep your consonants together. 10 minutes. We'll do, let's see, how many of these do we have? 21. So we'll go a little past halfway so that our Friday, I think this is a Thursday video, so that our Friday video is a little easier. All right, let's see. Consider the galvanic cell shown below, blah, 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 with some stuff. What is the standard for the cell? Okay, so now we are not at a standard cell, right? We're at a non-standard cell. They gave us some reactions here. They gave us chromium going to chromium +3, and they gave us bromine going to aqueous bromine with a platinum, whatchamacallit, platinum electrode, right? Platinum electrode. So it's still going to work the same way, but now we're going to have a Nernst equation situation where we'll need to deal with that. And so let's see, which one of these needs to flip? I need to flip this one. So we're going to go CR goes to CR +3 electrons. And so that's going to become a positive here. So the E standard for the cell, yeah, so E standard for the cell, they're not talking about these concentrations. So E standard for the cell, I should just get to do 1.09 plus 0.73 and get 1.82, which is this, because they said E standard, right? So that's kind of mean, because they definitely have set up a non-standard cell here, but they're saying what's the standard for the cell was everybody would be 1 molar, right? Let's see, which of the following statements is false? Electron, this is a galvanic cell. This is a galvanic cell. Electrons flow from the platinum cathode to the chromium electrode. So yeah, that's where we have a problem. So chromium is going from chromium to chromium +3, and then we're generating the electrons here. So the electrons are going not from the platinum electrode to the chromium electrode. They're going from the chromium electrode to the platinum electrode. So this is it right here. Reduction occurs at the platinum electrode. No, that is a true thing. That's just fine. The cell is not standard. That is absolutely true. To complete the circuit, cations migrate into the left half cell. So cations are going to migrate into the left. So we have positive ions going this way. So yeah, since electrons are flowing this way, we also need positive ions flowing this way, right? To balance that out. Oh, whoops. Electrons are flowing here. If negative charges are flowing here, then we need positive charges flowing here also. So where it says here, cations will migrate into the left cell and anions will migrate into the right, that is accurate. So now E standard for the cell, now we've got a Nernst equation kind of thing. So we're going to do our standard cell, 1.82. Is it plus or minus on that? I think it's minus. I'm going to have to look that equation up on the Nernst equation real quick. Give me just 1 second. Okay, so it took me a second. I had to go find the equation. I couldn't remember if it was a plus or a minus on that, right? But it's minus 0.0592 over N. N is the number of electrons in the balanced equation here. So since we have 3 here and 2 here, we can't just add those together and get 5. We'd have to go least common multiple, which is 6. There, times the log of Q, and Q is products over reactants. So if we go back up here, our products are chromium, so 0.2 for the chromium, and the other product is Br minus times 0.1 over reactants, which is bromine, which is 0.5. Now all of these are to different powers, right? So we doubled this one. This one was times 2, so that's going to have to be squared, and this one was times 3. We can see that, right? Yeah, times 3. So the 2 times 3 for that, so that's going to be to the 6th power, and then the Br minus or Br2 would be to the third power, right? So that's all kinds of goofiness there. Right, so I'll plug that in. I probably wouldn't give you one quite that nasty on the test, but right, it's products to their powers divided by reactants to their powers. So 0.2 squared times 0.1 raised to the sixth divided by 0.5 raised to the third. We're going to take the log of all of that mess, and then we're going to, so when we do that, kind of show you what I was punching in there, right? I don't know how well you can see that. So you should get negative 6.4. Oh, that's a really big number. Oh, yeah, time, because we're multiplying that. Times 0.0592 divided by 6. So it is 1.82 minus a negative 0.064. So those are going to be added then, right? Because you've got two negatives. So 1.82 plus 0.06 is going to give us 1.88. D for an answer on that one. Okay, we're at 15 and a half minutes, and there is zero chance that that I'm going to keep you at this point. So we'll go ahead and pause there for today and move forward tomorrow.